right, so I'm Dave Dykstra for Fermilab, and talk to you about Singularity with High Throughput Computing. I'm assuming most of you are familiar with high performance computing, but not so familiar with high throughput computing. So I'm going to first tell you a little bit of background on that. So with high throughput computing, we talk about it as being sustained computing over long periods of time, as opposed to with HPC, you tend to have more really great performance for relatively short periods of time. And with HTC, then it's usually embarrassingly parallel applications. So it's very easy to spread them out over lots and lots of widely separated CPUs, and usually either single-threaded or low number of cores threaded within each node. And it's based on commodity and relatively inexpensive hardware, and a lot more like most of the commercial cloud resources. And also distributed HTC is when we have those distributed all over the world. And there's first of all, there's no shared file system. So that's a big difference with HPC. And the users have to ship the input files and some of their software with the jobs. And also a very big aspect with HTC is we have a lot of opportunistic use. So we don't have any allocations. It's basically they're the resource owners of the different pieces all over the world, and they get priority on those machines. Everybody else kind of competes fairly for everything else that happens to be unused. And so just put your jobs in the queues, and whoever gets to them first gets to them. And the applications then, they can, especially the ones with long run times, they can be preempted if the owner wants to use their own computers first. The other ones get kicked out. And so that's why applications have to be relatively short or support being able to be restarted. So now we'll talk the Open Science Grid. This is the framework for the large-scale distributed HTC. It's really for resource sharing. It's addressing lots of aspects of technology, policy, social requirements of sharing. OSG itself doesn't own any of the hardware. It's the collaborations, the consortium, and it supplies some software and some services for tying these all together. And so this is researchers, universities, national labs, computing centers all across the US. We have, so the OSG project itself is funded by the NSF. A lot of the clusters are individually funded by the NSF for different projects, but not all of them are. And there's about over 100 sites in the US that tie all together with the Open Science Grid. So that's computing and storage, right? So I'll also talk about the WLCG, the Worldwide LHC Computing Grid. So this is our HTC for worldwide. It's really focused on the LHC, the Large Hadron Collider projects. And so in addition to the OSG, there's about a similar, I don't have the numbers for that, but I think it's roughly a similar amount of resources in the rest of the world as the OSG. So they talk about, they have 170 sites, so maybe it's a little less than what we have in the US. So they have 70 sites, so that includes the OSG, these 170 sites. Maybe not all of it, but most of it. And in 42 countries. So 41 countries have about the same as what the US has. We have a lot of money in this country. So it's really what drove the design for this whole thing was the fact that there are so many different countries, and they all wanted to be able to contribute to working on the LHC. They have researchers who want to be part of the research collaboration, but they want to spend their money inside their own countries. So that's why they want to have the computers there, and and in the U.S., they could have, if it's funded all by one person, by one organization, by the U.S. government, they could have spent it all in one place. But they decided, hey, as long as we've got the software and the architecture for distributing it, let's get all these other universities involved. spread out the knowledge, you spread out the work, and it's really a great way to build the community and the collaboration. And I wanted to point out that so there's like 50 to 70 petabytes of data just from the LHC, and this is expected to grow significantly, especially in 2026 when the high luminosity LHC comes out. There's going to be another jump in factor of 10 of data at that point. Meanwhile, it's growing at a kind of Moore's Law type of rate till then, and then there's going to be a big jump of 10 in 7 years. Really, the OSG was really initially inspired because of these high energy physics projects, and a lot of the funding, even for the resources, came to spend on those projects, especially the two biggest ones, CMS and Atlas, and they're still the largest users of the OSG. So CMS uses about half the resources of OSG. And Atlas, I think, is about a third, and everybody else the other, sixth. But there's a lot of other users, a lot of other smaller users, a lot of different disciplines, energy physics, biology, lots of other users of the OSG as well. So talk about the scale. So this is the OSG again, not LWLCG. And so we like to speak in terms of CPU hours because it's sustained. More than cores, but so it's been about 4.5 million CPU hours in the past year per day, which if you divide that out by 24, that's 190K cores. Which you think about most of your HPC, you say, well, that's not that many compared to HPC systems, right? But just the fact that it's distributed and everybody can use it, and plus the fact that it's this collaboration is still very, very valuable, and it's also the fact that people don't need to do any allocations, just submit your jobs and they get done. Of course, it's not infinitely scalable, so people who know that they need to have 200K cores aren't going to submit their jobs here. It's just not going to work. So, yeah. So the model is submit locally, run globally. So, wherever you can submit from right in your university, and the jobs will run all over the place. So, for example, OSG sites and also Exceed sites and EGI. I didn't speak to it. I had it on the slide. I think that EGI is basically the collaboration in Europe, corresponding to OSG, and it can also go to cloud resources. Of course, the Exceed sites and require an allocation, and the cloud, you got to figure out how to pay for it. So now getting into Singularity. So our motivations for using Singularity in the HTC is, well, a lot of it is for security. So we use unprivileged pilot jobs. So first, the pilot jobs, since they're all over the place, what they do is individual experiments. They will send first in their pilot jobs to make sure they allocated the resources, and then those pilot jobs go back out to the central and pick up their user jobs and run them. And so a lot of cases, a single pilot job could be running jobs from a lot of different users, and we don't want them interfering with each other. So the isolation was very important to us, to be able to use the IPC and PID to have separate namespaces, and also the file isolation with the contain option. And also, of course, having that consistent environment is very nice, so you don't have to worry about which operating system version people are on and what base operating system packages are available. That's very useful. Now, so the image contains a decent baseline of software, and especially with defaults, we get them all on all the default image. We get it the same on all the sites. We also like the advantage that different experiments can have a custom operating system environment with the different container. Now, we do keep most of the application software outside of the containers. I'll talk a little bit more about that in the future slides. And then also the enabling special environments as GPUs. Vast majority of the jobs don't use GPUs, but we are starting to get to get more of that, and some of the resources do have GPUs. So to talk about the container life cycle, is they're all relatively short. They last a few hours and they're gone. So each job gets a separate container instance, and then they're gone when the job finishes. Again, application software mostly outside of the container. So here's just a plot of the Singularity instances per day. Basically, it's been about 500,000 per day of Singularity starts over all of the OSG. And this doesn't include CMS. It doesn't include the big projects yet. So another slide for CMS is about 1 million per day worldwide. So probably about similar amount on the OSG, about 500,000 per day, and another 500,000 or so on the rest of the world. And also there is some, again, saying there is some GPU usage, and here we're talking about an average about 1K cores, but also on the list some of the names of some of the other projects. We have Ice Cube and Lego. Lego's not on here, but they're another big user. And of the OSG, they're just not using the GPUs. So now we have the problem. So we have all these containers. We don't have any shared storage. Let's say, just for calculations, we get an average of 5 gigabit size of a container, times 1 million for CMS and 500,000 for the rest of the OSG. We're talking 7.5 petabytes per day, just if we would ship around those entire containers everywhere. So we need a much more efficient way of distributing that. So what we use is the CVMFS, the CernVM FileSystem. Now this predated the use of containers. We'd already had, this is invented for high throughput computing by CERN. You can publish centrally, so and the central location can be anywhere, but you can publish in one place, a new release of software, and then it becomes basically immediately available everywhere around the world. And you can then do an LS, anywhere in the world, and you see the files. They look like they're there. They're not actually there. They just look like they're there, and as soon as you try to read them, then it will download the files on demand. So it's quite reliable. All kinds of different multiple points of failure. We have caching. It's heavily cached. And it's read-only at all the sites, so you just publish it centrally, and then everywhere else it's read-only. And it's used for software, especially. Also, some kinds of data gets distributed there. It's available everywhere. OSG, EGI, and a couple of the Exceed HPC systems have it so far. And it's a fuse module. So let me say more about the features. So it's, as I said, they're immediately available. They look like they're immediately there and the metadata operations are all done on the worker node, so on catalog. So whenever you try to access some files, it will download a catalog, which is actually an SQLite file that's all behind the scenes, and then it points to the names of the real files. The files are stored named by a secure hash of the contents of the file, so they by definition never change, and also we have the secure hash of it for security purposes. And they also get deduplicated. There's an awful lot of duplication on different releases of software. There's an awful lot of files that are the same in each release. So they get shared, so that saves a lot of space. And they also get compressed for storage at the previous. I showed there's Stratum ones at major sites. That's where we keep a copy of all the. So copies get kept at a couple sites per continent, basically, and there it's all stored, compressed and deduplicated. So then also over the network it's compressed, and then it's also cryptographically verified with one digital signature on a very small file, so it's very low overhead there, and then all the secure hashes from then on make sure that nobody has tampered with it along the way. Also, larger files get broken up into about 8 megabyte chunks, and by default, and that's to smooth out the load on the servers. It's not to improve performance. It's to keep the servers from getting overloaded. And Yeah, I talked about the Stratum 1 servers. It's also cached at each site with the HTTP proxy caching, which is the SQUID open source project. And it's cached on each worker node. So there's a space, it's typically expected there to be a local disk. In our cases, we always do. I know that's not always the case on HPC. But then all that caching really greatly reduces the latency and the bandwidth used for transferring. And there's also an optional external data server modes. This is for larger data files and that are partially reused. They're not used on every, like with the software, every node is accessing the same. Every node in a batch of jobs is going to access the exact same things. This is more of a case where some of the files get reused some of the time, and then the metadata is still used, goes through the regular normal paths, but when you actually go to access the data, it goes off to different servers, which may not be on your site, but it's kind of geographically distributed. There we have like a dozen of these sites currently around the OSG at major universities. Here's an example of some of the names. There's a whole lot of different CVMFS repositories. Within each repository, a different organization has the ownership of it and has the rights to publish to it. We also have one in particular I'm going to talk about, the singularity.opensciencegrid.org, which is just a place for holding Singularity containers. And what it does is we go ahead and define the containers in Docker, but we execute them with Singularity. And meanwhile, we take them out of Docker and publish them in this CVMFS repository through this tool, CVMFS Singularity Sync. So yeah, here's the picture of how it works. So the user first puts, in GitHub, there's a file which says what the name of Docker, which Docker images do we want to publish. And then the user can publish either directly to Docker or via a GitHub to get into Docker Hub. And then it automatically syncs and publishes into the Singularity repository. So once we set up the configuration, then whenever the person who owns that container in Docker Hub publishes a new one, it gets automatically published in CVMFS. And then it's just automatically available there on whatever system you want to use it. So yeah, we store container images on CVMFS in extracted forms, and not big monolithic files, but Singularity calls this sandbox mode. And so we unpack them. And so the result is that since we only only download on demand the individual files, then as soon as we end up taking only a very small subset of the actual published files that get downloaded to each node, and it's not all at the beginning. It's as it uses it over time. And we don't care about the individual Docker layers because it all gets deduplicated anyway. So now I want to compare what happens on HPC systems versus with CVMFS. So if you have a locally high-speed file system where you can mount a file, then what Singularity does is it mounts the whole file as a loop on the client as a loopback file system, and this moves the metadata operations from the metadata server and the file system. This is really, I think probably that by itself is probably one of the big sales to the HPC admins, right? Because they don't kill their metadata servers with all these files. And it also, other huge advantage is it only reads the pieces that are actually used out of the file system. So you may have a very big image file, but it only reads small pieces of it out of the file system, so the bandwidth is down. So CVMFS does this too, as I mentioned. But the difference really in our case is that CVMFS, the files are instantly available worldwide. But so far, most of the HPC administrators are suspicious of this Fuse file system. So far, we've been mostly building image files to use the HPC allocations CMS and Atlas have. That's what I'm most familiar with. Now, the application software is much bigger than the OS code. And like I said, normally we bind mount /CVMFS into the container and just use the application code directly out of there and not put it into the container. But for the HPC systems, we need to have it all in there. So, both CMS and Atlas, they end up making about 200 gigabytes. Somebody was talking about 50 gigabytes being huge, right? Well, they make them more about 200 gigabyte files. And it takes like 8 to 12 hours to build them, reading it out of CVMFS, just a subset of the pieces of CVMFS that they think they might need for all the different jobs that they might be taking while they're running on their allocation on the HPC system. So yeah, it's a big hassle. We would much rather people would install CVMFS on the HPC systems. But also these containers typically include the pilot. So, which means that we can't let the pilot run Singularity because it's not nested. So that's another disadvantage that when you have this type of thing with all the we can only run this what we call production jobs, which is run by the central team, and they share the user ID, and we can't take jobs from all kinds of different users because then they would be not isolated from each other. So let me also talk about our push towards unprivileged Singularity. So because we don't need these loopback mounts, and we can avoid using overlay FS by in order to have extra bind mounts that it might not be in the image, we instead use underlay. So that's why the underlay feature, which is why we came up with that idea first, because that was really important to us in order to be able to allow us to run unprivileged. So that means we can now in Red Hat 7.6, which came out last fall, we can now run Singularity without set UID at all. So we reduce our risk that much more and not be vulnerable to the CVEs that come with that. Now there is some risk with using unprivileged namespaces. It's not enabled by default on Red Hat 7.6. You still have to set a system parameter to enable it. But we think that there's a lot more people watching that, and then there are looking at Singularity code, so we think that the risk is lower then. And just to mention, for those of you who aren't familiar with the underlay feature, it works by first bind mounting everything requested on the command line. Every bind mount requested, we first put that into a scratch space, and then bind mount everything from the image on top around that without anything. So that way we only have to have that one space that becomes the bind mounted into the root file system inside the container, and don't need to use the overlay FS. Also, just to mention also that in the most recent Linux kernels, it's not yet in Red Hat Enterprise Linux, but they can also it also allows mounting fuse file systems in unprivileged namespaces. So we're looking forward to that maybe someday we'll be able to use that to mount CVMFS inside a container without having to ask. But it's still going to be quite a few years probably before they get on HPC systems. Okay. Of course, we were 15 minutes ahead of schedule to begin with, but I only have one more slide. So this is it. I also just to mention that in Enterprise Linux, probably most of you are familiar with it, but just WLCG has standardized on Red Hat Enterprise Linux, and its derivatives, Scientific Linux and CentOS, and EPEL then is the extra packages for Enterprise Linux, and it's really part of the Fedora project, and it adds packages for RHEL, and now OSG has their own software support team and Yum repositories for packages they distribute, and so does EGI, but they both kind of depend on EPEL. When things are in there, they'd rather use it in there. So when the original supporter of Singularity and EPEL lost interest, then I ended up volunteering to take that over. So I'm the EPEL administrator owner of Singularity as well. And just so currently it's installed in Fedora. I installed it in Fedora, but not Singularity 3. I mean, Singularity 3 is now in Fedora. Singularity 2.6 is still the current one in EPEL, because there's still a lot of people depending on and using it in production, and I haven't heard enough from enough people yet that Singularity 3 works for them. In fact, there was one that we knew of that was causing a problem, and that was just fixed, and the latest branch should be in 3.2. So it looks like 3.2 is looking pretty good so far to be able to get put into EPEL, unless we hear from somebody else finding another issue with it that's going to break their production use. So that's it. So questions?
Yeah, so is it still HT-Condor CE, the one that is used as a gateway for?
Okay, well, HT-Condor CE is the most popular one in the Open Science Grid, but it's not the only one. So yes, so HT-Condor CE, and like the principal investigator who started OSG is also the same one who is the leader of the HT-Condor project, so that you got a lot of synergy there. But yeah, it's become more and more. I've been seeing people giving up on other CEs and using HT-Condor CE because it works better for them. Also, all that pilot stuff I mentioned, most of the pilot work uses another copy of HT-Condor. So it's kind of like another system that people submit to an HT-Condor system, and then the pilot becomes an HT-Condor client, basically, and jobs get run through that. So even if the CE isn't HT-Condor, we still often have HT-Condor involved.
Okay, because HT-Condor has some support in the script for Singularity jobs.
Yes.
So I'm not sure about the
It's not working very well yet, but
yeah.
So far, it started out at each individual project. CMS started out with their own Singularity script, and then it's getting moved into Glide and WMS, which, as I said, is the project that's using HT-Condor inside it, and then the plan is to move it back to HT-Condor. So it will be, once we have it working, everything well, probably HT-Condor natively will be supporting it well for us. So.
One other last question about the CVMFS. Any plans for, or any management of version control? Because you will deal with Singularity containers as files.
Individual files, but I mean, yeah.
For the software releases,
Well, inside for the application software, that's usually already managed separately by each project. So, yeah, like in CMS.cern.ch, there's different releases of all the different versions and they're all in there. They're all in there. So whichever one that people want to access, they use. Yeah. So for the operating system, typically, for the container, we just use the latest version. It actually, it does change the name when the new version comes up, but then that still becomes the current one, right? So symbolic link.